right, well, let's go ahead and begin. First with a couple of announcements. Your next homework assignment is due on Tuesday the 22nd, so you still have plenty of time available to work on that one. Homework number 3 includes atmospheric pressure variation, which we've had some practice on in our last class meeting on Thursday. It includes manometer problems, which you've also practiced last time on Thursday. And then it has some questions related to hydrostatic forces on flat surfaces. And that's what we're going to be discussing during today's class meeting. Those of you who are in the lab got a sneak preview of hydrostatic forces last week during the lab, where in lab 2 we actually did the physical measurement of hydrostatic forces. So for those of you in the lab, I hope that you've already received my email where I was letting you know that the report for lab 2 isn't due until Friday at 4 p.m. And I made the decision to give you a bit of extra time for that particular report simply because I wanted you to have the additional practice on hydrostatic forces that we're going to get in today's class and Thursday's class. So maybe you've already finished those calculations completely and are ready to submit your report, but in case you're not, hopefully today's class meeting and then a little bit of additional information on Thursday will help to clarify some of those concepts. The other thing that I told you in the email that I sent yesterday was that for today and tomorrow's lab activity, you need to download and install the EPANet software. So if you haven't done that already, please do. I think that many of you have a laptop and will bring it to today's lab, and that's great. If you don't have access to a laptop, maybe you only have a desktop computer at home, that's okay. You can observe the demonstration that I'll be doing in today's lab. And it's not quite as good as following along yourself, but seeing it will be a help, and then you can work on it at home. All right, so before we talk about hydrostatic forces on flat surfaces today, are there any questions related to the announcements? Okay, if not, then we will move forward talking about hydrostatic forces. Now, what if someone has a Mac? If you have a Mac, you're going to find that semester after semester, your computer isn't compatible with the engineering software that you need to use. And so my suggestion is that you should use an Apple product called Boot Camp that allows you to install a secondary operating system. And as an engineering student, you have access not only to Microsoft Office, but also you get a free copy of Microsoft Windows. And so you need to set up a dual boot system on your Mac if you want to be able to install EPANet, if you want to be able to install a lot of the software that later on in civil engineering, unfortunately, there just aren't Mac versions for a lot of engineering programs. Okay, and I have instructions that explain a little bit on how you can obtain Windows and the link for the dual boot. So I'll send you that information related to how to set up Boot Camp on a laptop. All right, so one of the key ideas that goes along with finding hydrostatic forces is the centroid and area moment of inertia. And hopefully this is familiar territory based on the classes you've taken before. I think if I remember correctly, when I was in statics many years ago, that's when we were introduced to centroids and area moment of inertia. Your textbook has the formulas for several different shapes. This figure is illustrating those same formulas, and the two shapes that become most important for us in this class in fluid mechanics are the area moment of inertia for a rectangle and the area moment of inertia for a circle. And so I first of all just wanted to point out what those formulas are. So for a rectangle, area moment of inertia is AB cubed divided by 12. And so A is the horizontal width and B is the vertical length. And so when a plane is oriented in water, whether it's straight up and down or even if it's inclined at an angle, then it's the horizontal width that will assign the parameter A, and then it's the vertical length that will assign the parameter B. In the case of a circle, the area moment of inertia is related to the radius of the circle. And so you can see it's pi r to the fourth divided by 4. And so the units for area moment of inertia are length to the fourth power. All right, so just keep that in the back of your mind through today and future class meetings, is that occasionally we're going to have to refer to these formulas for the area moment of inertia, which we give it the variable I. And that's the area moment of inertia about a horizontal axis that we're interested in. All right, so this is the type of problem that we're working to address in Chapter 3. Chapter 3 of our textbook is all about hydrostatics. And so consider if you have a gate that's holding back water. And you can see that there are some dimensions here. This is a gate that has a vertical dimension of 4 meters. And then above a hinge is a meter of air in contact with the gate. But it's, so the gate itself has a total physical length of 5 meters. But the submerged length of that gate vertically is 4 meters. So why is this, what's the purpose of the gate? Well, the water is going to be pushing to the side. We know that the further down we go, the pressure is increasing. And the rate of the pressure increase, the slope of that line, because it is a linear increase, the slope of the line is gamma, the unit weight of the liquid. And so pressure is increasing at a rate of 9810 pascals per meter of depth. And so as the pressure is going up, there is a force that's pushing to the right on that gate. And so presumably we would have to apply some sort of a torque or a moment about that hinge, or maybe a force would need to be applied at the bottom. There could be a stop block put into place to try and keep that gate from opening up. And if it opened up, then the water would spill out. So here is the front view of that gate where we've assigned the dimensions A and B. And so you can see that it's from this side view that we get the dimension B equals 4. And so that's the vertical component of its distance. And then the horizontal component we get from the front view. We don't necessarily know when we're looking at the gate from the side how wide it is. But now we can see with this front view that the width of the gate is 3 meters. So even though the gate's physical height is 5 meters, it's only the depth underneath the water line that is interesting to us and that we assign to B. So if we want to find out how hard is the water pushing on the gate, then we have to know, first of all, the dimensions of the gate. We need to know the properties of the liquid, so that it's water tells us the unit weight. And then we also need to do an analysis related to some other factor as well. But this is kind of just the preview of what we're trying to figure out, is what's the effect of the water on that gate. Now this is showing the linear increase in pressure. And so you can see that there is a triangular shape here. It's shaded in green. And the reason why that's a triangular shape is this is showing the pressure as we go down through the fluid. And so when the air and water are in contact with each other, then that means that the water has the same pressure as the air at the interface. And so let's say that we're talking about gauge pressure. And so that means that the air pressure is 0 right at the surface. So the pressure is 0, and then the pressure is increasing linearly. The further we go down, the pressure is going up. So this triangular shape illustrates the increase in pressure with depth. And so force is pressure times area. But it's not just as simple as, we can calculate the area underneath the waterline pretty easily. The area is 3 times 4. So the submerged area is 12 square meters in this case. But which pressure should we use? Because the pressure is varying with depth. And so it's not just as simple as we might hope. There's an intermediate step. And what we're going to have to do, as you'll see, is find the pressure at the centroid. And the reason why we're doing this is oftentimes it's convenient if instead of considering the pressure distribution, it's convenient for us to understand what's the equivalent force. What's the magnitude of the equivalent force and what's its location. And so here in brown, you can see that I've indicated that there's some equivalent hydrostatic force acting on the gate. So that's what F stands for. It's the hydrostatic force. And in reality, there's not just one single point force that's acting on the gate. But if you integrate the distribution of pressure over the area, then the effect of that integration is the same as a single point force located at this depth. In the case of a triangular distribution, the location of the force would be 2/3 of the way down from the water. I should have made that a trivia question for those of you who were on the lab last week, because I told you about this triangular distribution last time. But for a triangular distribution, the center of area is 2/3 of the way from the surface. And so F is just the equivalent of finding the force distribution, the pressure distribution acting over the area. Now, the centroid of the gate itself, you can see, is now shown with that red dot. And so centroid is the center of area. And the reason why it's important for us to know what is the location of the centroid is that if we find the pressure at that location, then it helps us to determine the magnitude of the force. So here's another thing that we're going to try and analyze whenever we're faced with a hydrostatic force problem, is we're trying to find out what's the dimensions of the submerged gate. We're going to find out what's the location of the centroid, because whatever the hydrostatic pressure is at that centroid dictates the magnitude of the hydrostatic force. Not the location yet, just the magnitude. So we'll get into all the details of this, but just step by step, I wanted to show you some of how we, deconstruct the problem and find the applicable pieces that we're going to have to analyze. So the center of area of the submerged portion of the gate is what's interesting. And so you'll see that this red dot, it's not the center of area for the full physical gate. It's just the centroid of the submerged portion. So it's intentionally offset a little bit further down below the physical centroid of the gate. It's the centroid beneath the water surface. And so it would be 1/2 of B is the depth to the centroid. Any questions so far about this material? All right, so here is a triangular distribution of pressure, starting at 0 and linearly increasing as we go down through the fluid. Triangular if the gate starts at the top of the water surface. Sometimes the gate is below the water surface. In other words, it's fully submerged rather than partly submerged. In this example, the gate was only partly submerged. Now in this next one, the gate is fully submerged. And so again, we have a side view of the gate. We have the front view of the gate. You can see that we're calling the width of the gate A, its height we're calling B. And if the water line is above the top edge of the gate, then what that means is that the centroid is still in the same place. That doesn't change the definition of centroid. In this case, the centroid is still the center of area, and the entire area is submerged, And so the physical centroid and the submerged centroid are in the same location. But what's different is that the pressure distribution is no longer just a simple triangle. Now we have a trapezoidal distribution of pressure, where at the top edge of this gate, the pressure isn't zero because it's down below the water surface. And so it starts at some positive amount of pressure here, and then it continues linearly increasing. And so the hydrostatic force, the location of that force, it's not just as simple as saying it's 2/3 of the way down the gate. You know, in this previous example, if the water is only partly submerging the gate, then the force location was 2/3 of the way down. Now in this case, the force is a little bit closer to the centroid than it was before. And so there's a different technique used to find the location of the hydrostatic force. The magnitude, though, we can still find the magnitude of the force the same way that we did in the previous example. And that is, you ask, what is the pressure at the centroid? And then the pressure at the centroid multiplied by the area of the gate gives you the magnitude. So the two things that we want to know in this case, number one, what's the magnitude of the hydrostatic force? Number two, what's the location of the hydrostatic force? So if we can find those two things, then we're in business. All right, so you'll notice that in a non-triangular distribution that the force location gets closer to the centroid. And if we take that gate deeper and deeper and deeper, then the location of the force is going to keep getting closer and closer to the centroid. And that is because, you know, if you're 1,000 meters under the ocean with this gate, then the force at the top and the force at the bottom are pretty much the same. The percent difference between the force at the top and the bottom is very small if you're deeply submerged. And so the location, you know, the gap distance between the centroid and the point of application for the hydrostatic force, that gap distance keeps getting smaller and smaller the more deeply submerged the object is. I'll give you a formula today that'll allow you to always predict accurately the location of the force. All right, now I've rearranged this slide slightly compared to that which you may have printed out. So what we're looking at here is a tank of water, and this is the side view of a gate. And how is it different from this gate? Let's call it the same gate, but now instead of being vertically oriented, we've tilted it onto the side. So it's still just a rectangular gate, but tilted onto the side. And the reason why it's tilted on the side is we're going to go through some definitions, some variable definitions, and having it tilted on the side illustrates why we have to keep track of certain things separately rather than combining them. Okay, so F is still the hydrostatic force like it was before. You can see the red dot identifies the centroid, so that's the center of area for the gate. And the centroid for the gate, it doesn't change whether it's vertically oriented or if it is at an incline or if it's horizontal. As long as that gate is fully submerged, then the applicable centroid that we have to identify the location for, it stays the same on the gate. So delta H is the vertical distance from the centroid to the water surface. And so what we're looking at is we're looking at a tank that's all the way full. And so delta H is from the water down to the centroid being the center of area for this shape. Okay, that's delta H. Now, Y bar measures the same starting point, but instead of going vertically to the surface, Y bar follows the same angled path as the inclined gate up to the surface. So I think it's pretty obvious what Y bar is. Now Y bar is just follow the same angle up to the surface. Now if the gate is not at an angle, if the gate is straight up and down, then delta H and Y bar are the same. If it's vertically oriented, Y bar equals delta H. But in this illustration, since it's at an incline, Y bar is larger than delta H. Now you're going to have to revisit some of your geometry skills. Maybe you haven't thought about geometry since you were in the 9th or 10th grade, but in order to calculate the length Y bar, sometimes you'll be given delta H, or you can find it based on the dimensions that are provided. And then you'll have to calculate Y bar. So you'll use sine or cosine or, like a similar triangles analysis. You remember the 3, 4, 5 triangle, those sorts of things. So it may be a little bit rusty. It's rusty for me, and I kind of look at this same kind of geometry every year. So I kind of always have to remind myself how to calculate these inclined distances, but we'll get through it together. YCP is inclined distance, as you can see. So it's this angled distance, and it's from the water surface down to where the force is located. So CP stands for center of pressure. So the red dot, the centroid, that's the center of area. But the center of pressure is where the force is located. So if we go back to this first example that I showed you, this one, the center of area is at the centroid. I just heard an odd echo. Did my computer freeze up for a second there? Can you hear me okay now?
I can hear you.
Okay, thanks. The force is located at the center of pressure. And so, if you find the centroid of the triangle represents the pressure, and so the centroid of that is where the force is located. So in this diagram here, the force was located at the center of pressure. And so the centroid of this trapezoidal distribution is where the force is located. Same thing is true here. The force is located at CP. Now, you'll notice that there's this offset dimension here. This little dotted line is just because we can't put the variable and the arrows right on top of what's already there for Y bar. And so, it doesn't mean that you need to go some distance down. It's the same length as if you start at the water surface and you go down inclined path to where the force is located. So there's a formula that allows us to calculate YCP. So here are those definitions. Delta H is the vertical distance from the centroid to the water surface. And that is important because that's going to tell us the magnitude of the force. The force magnitude is determined by what is the pressure at the centroid. And so the pressure at the centroid we can calculate with the hydrostatic equation. Hydrostatic equation is depth multiplied by the unit weight of the fluid. Y bar is the inclined distance from the water surface to the centroid. YCP is that same inclined path, but it's from the water surface, not to the centroid, but to the center of pressure. So the force is located at the center of pressure. All right. Now here's the formula that you can use to calculate what is the distance along the inclined path from the water surface to where the force is located. So remember from our sketch here, YCP is the inclined distance from the water surface to where the force is located. Okay, so here's the formula for that. Y bar plus I divided by Y bar A. So Y bar is the slant distance to the centroid. So that's the inclined path from the water surface down to the center of area. I is area moment of inertia, and we looked at some of those formulas already today. That was the second slide today, right after the announcements. It's when we were looking at the area moment of inertia. And A is the surface area of the submerged portion of the gate. Now, this isn't on your slide, but you should write it in the margin. All I've done here, oh, I guess we don't really need the plus. There we go. Plus is implied. All right. So this comes from just moving the Y bar to the left-hand side of the equation. So what this equation on the right, it's the same thing as the equation on the left. The equation on the left is to find out the distance below the water surface along the inclined path to where the force is located. This is asking what's the distance, the gap distance between the centroid and where the force is located. So what this equation is going to tell you is how, okay, wait for it. All right, here. The distance along the inclined path from the center of area to the center of pressure. And so how far is the distance from here to here? I divided by Y bar times A is this distance. And that shortcut or that simplification is pretty important if you're doing like a moment analysis. You know, for example, if there was a hinge at the centroid, then you may want to know what's the applicable moment distance. And so then you'd need to know how far is it from the center of area to the center of pressure. So that's why I just wanted to point out this little rearranging is that the gap distance is I divided by Y bar A. So keep that stowed away for the homework assignment. There will be some problems where this equation will be useful. Okay, back to this original, I introduced this as the type of problem that we're going to solve this semester. So we said that it was 3 meters wide, 4 meters deep. This is water, so let's just say it's 20 degrees Celsius water, which would give us a unit weight of 9790 newtons per meter cubed. And so we're going to go through the process of calculating what's the magnitude and the location of the hydrostatic force. Now, unfortunately, for a lot of different reasons, we're not in the classroom together. What I often do is I write on the whiteboard the steps that you should follow to solve this problem. So since I don't have the whiteboard handy, let me just write that down. I'll start up a Word document, and I'll just type what the steps are, and then we'll look at how to go through those steps one at a time. Okay. So step 1 is we're going to find the distance to the centroid. And we're talking about delta H. Step 2 is find the pressure at the centroid. And that's P bar. 3, find the magnitude of the hydrostatic force, F. And 4, find the location of the hydrostatic force. And by that, what we mean is YCP. Okay, so maybe in the margins, what you can do is write down this step by step, find the distance to the centroid, pressure at the centroid, magnitude of the hydrostatic force, location of the hydrostatic force, and then it looks like in this problem, it's also saying that we're going to apply a reaction at F to try and keep the gate closed. Remember, when we looked at this before, we were discussing in terms of here's the hydrostatic force pushing from the left to the right on the gate. Well, the gate's going to open unless we apply an external force to keep it closed. So the hydrostatic force is trying to open the gate. In this example, it's asking, well, if we want to keep the gate closed, how big does this force need to be? And so step 5 is going to be find the magnitude of F. That is to say, to keep the gate closed. All right. So these are the steps that we're going to follow. Okay, first of all, distance to the centroid. Just by inspection, we should be able to know what is delta H. Anybody willing to venture a guess what is the depth to the centroid, the delta H that we're going to use in this problem? Reagan has it there. It's 2 meters. That's right. All right. So let me just gradually reveal the solution here. So I've done some setup and definition. A is 3 meters, B is 4 meters. We're going to need these factors when we solve the area moment of inertia equation. Just up at the top by the drawing, I'm saying that here's our unit weight for the water, 9790. Okay, so for us to find F, we're going to have to break it down into its component parts. And so here is the center of area, and that's of the submerged part. So delta H is 2 meters. Okay, so that was the first part. So delta H is 2 meters. The pressure at the centroid. All right, so you know the hydrostatic equation already. The hydrostatic equation is delta P is equal to delta H times gamma. So what is the pressure at this location that's submerged 2 meters beneath the water? If you've got your calculator handy, you can follow along. You're just going to multiply 9790 by 2. And that tells you the pressure down at the centroid. So you can see here the pressure at the centroid. We're multiplying delta H by gamma. So it's 2 times 9790 newtons per meter cubed. So the pressure at the centroid is 19,580 pascals. All right. Next, the magnitude of the hydrostatic force. So force is pressure times area. In step 2, we found the pressure. The area is 3 meters by 4 meters, and so that's 12 square meters. Okay, so the magnitude of the hydrostatic force is the pressure at the centroid multiplied by the area of the gate, so 234.9 kilonewtons. All right, the location of the force. Now, to find the location of the force, that's where we are going to, we could use the shortcut method and just say it's 2/3 of the way down. But let's prove to ourselves that the formula for YCP works. Let's test it out for the first time. And we can confirm it with that 2/3 of the depth thing. If it's 2/3 of the depth, then we can just calculate really quickly. If you multiply 4 by 2/3, it's going to be 2.67 meters down from the water surface. But let's try out this formula for YCP just to see that it works. All right, so that's what we do here for the location of the force. Okay, so since it's vertically oriented, since the plate is straight up and down, then Y bar and delta H are the same. If it was at an angle, then we'd have to use geometry to find out Y bar. But in this case, Y bar and delta H are the same. And now we also need to find the area moment of inertia. So you can see that I have the width parameter of 3 meters multiplied by the depth parameter 4 meters cubed, and then divide that by 12. So our area moment of inertia for this gate is 16 meters to the fourth. And so if we put that into the equation for YCP, then we get the same thing, the 2.667 that we knew from the 2/3 shortcut. We'll get that. And I'll give you a moment to confirm those calculations on your own calculator. So it's Y bar, the depth of 2, plus 16 meters to the fourth, divided by 2 times 12. Add it together, 2.67. All right, so now moment analysis. What we have is we have the hydrostatic force that is 2.67 meters down from the hinge, and so that's going to be a counterclockwise moment. The magnitude of the force multiplied by the distance is the counterclockwise moment, and then for clockwise we have F acting at a distance of 4 meters. So that's what's pushing to keep the gate closed. So is F going to be less or more than the hydrostatic force? Less. Gavin's got it right. So we do that moment analysis. We say, here's the point of application for the hydrostatic force. So that is the 234.96 kilonewtons at a distance of 2.667 meters from the water surface. And then that is counterbalanced on the opposite side, trying to achieve clockwise rotation is our stopping force. And it's going to need to be 156.64 kilonewtons in order to keep it closed. So I think that's a pretty good illustration of not only the process, but also how to use all these equations. And as long as it's a flat surface that you're finding the hydrostatic force on, the same method is applicable. It doesn't matter how deeply submerged, if it's vertical or inclined, it's the same basic method. It's the same structure that we're going to apply. It's just, you know, if it's inclined, then delta H isn't equal to Y bar. It's only when it's vertically oriented that those two are equal. If it's a circular plate rather than a rectangular plate, we'd simply have a different formula for the area moment of inertia. But the same structure where first of all you find the distance to the centroid, then you find the pressure at the centroid, then you use the pressure at the centroid to find the magnitude of the hydrostatic force, and then the location of the force. You know, that same, the bones of our analysis follows the same approach. Any questions about this example before we move on? Okay, let's get some more practice. And this time, I'm going to pause and give you a moment to apply that same technique to this gate. All right, so this is a little bit different. Now, it's still vertically oriented. So the fact that the gate is straight up and down means that delta H and Y bar are going to be equal. So that's nice. But now, it's not the gate doesn't go all the way up to the surface. And so we're not going to be able to use the 2/3 of the distance thing to find out the location of the force. Okay, so the problem says a gate is 3 meters tall and 2 meters wide. So what that means is that it's 3 meters from the shaft down to the bottom of the gate, 3 meters, and then 2 meters into the page. So that's a dimension that we'd only be able to see if we were looking at the gate from the front. Okay, so it says it's holding back water at 20 degrees Celsius. So that tells us the unit weight is 9790 newtons per meter cubed. And the height of the water, H, is 6 meters. So from the water surface to the bottom of this tank is 6 meters. So the gate itself is 3 and H is 6. I guess maybe H isn't drawn to scale because it looks like maybe we'll just have to rely on the dimensions and not our perception of those distances. Okay, the problem is asking to find the magnitude and the location of the hydrostatic force acting on the gate. So the process here is identify the location of the centroid. Like if we look at what was our solution in the previous example, find the distance to the centroid, find the pressure at the centroid, find the magnitude of the hydrostatic force. You can use that same technique here. So you're starting off with find the depth of the centroid, then the pressure at the centroid is the depth of the centroid times gamma, magnitude of the force, and then to find the location of the force, you have to use the formula for YCP. All right, so I'm going to pause here for a moment and to give you probably 7 or 8 minutes to work through it. You can type your guesses or your intermediate calculations into the chat window along the way, and I'll confirm or deny whether you're in the right direction. And then after a few minutes, then of course I'll start to go through the solution. So I think it'll help to set it into your memory if you actually go through these calculations on your own and not just wait for me to show you, but you'll be more engaged and you'll retain the information if you try it out now. Hydrostatic force so far. No, Casey, that's a bit too deep. Let me get us through to the magnitude of the hydrostatic force. No, Peter, not quite that much. The dimensionings are tricky on this problem, right? Let me find the right one here. Bring it over. All right, so the water depth is 6 meters, and so the delta H is going to be okay. So if it's 3 meters from the top of the gate down to the bottom, then that means it's 1.5 meters. Oh gosh, it's 1.5 meters here from the hinge down to the center of area. And so that means 1.5 plus then from this distance is 3 meters. Okay, so delta H is 4.5 meters. In other words, the way that I set it up down here is I said, here is the centroid, and it's 1.5 meters from the bottom. So delta H is 4.5 meters. That means that Y bar is 4.5 meters since it's vertically oriented. Okay, so now that I've talked through it, does everybody see the delta H is 4.5 meters? Because it's 6 meters from the top of the water down to the bottom of the tank. That's 6. And then if we divide the gate into half, that means it's 1.5 meters from the bottom to the centroid. So 6 minus the 1.5 means that from the water surface to the centroid is 4.5. All right, so that gives us delta H. The pressure at the centroid, you can see I've just multiplied delta H by gamma. So that gives us 44,000 pascals at the centroid. And then the magnitude of the hydrostatic force is the pressure at the centroid multiplied by the area. So 264.3 kilonewtons. Okay. Gavin, I think I might have given you the thumbs up prematurely. I got to check my eyes. Sorry about that. I said yes, and it wasn't quite right. Hopefully that didn't send you down the wrong path. Okay, so the pressure at the centroid times the area gives us to 264.3 kilonewtons. All right, so any questions about the solution that I showed so far? Feel free to type them in the text area, or ask them. You can unmute your microphone if you've got a question. I'm always glad to hear a human voice. Any questions? All right, now that's the magnitude of the force. What we also need to know is the location. So to find the location, we have to solve for YCP. And one of the things we need to solve YCP is I, the area moment of inertia. Okay, so the location of the force requires us to solve for the area moment of inertia. So A is 2 meters and B is 3. So A is the width and B is the depth parameter. So the problem said that the gate is 2 meters wide and 3 meters tall, and it's fully submerged. And so it's the full physical height of the gate that we're going to use is B. Okay, so the area moment of inertia is 4.5 meters to the fourth. And then we can substitute that into the formula for YCP. And so Y bar was 4.5, and then the location of the hydrostatic force is a little bit further below the water surface. It's deeper than the center of area. So the center of pressure is always going to be a little bit lower than the center of area. And so that additional distance below it is the result of I divided by Y bar A. So you can see that it's going to be, in this case, an extra 0.1667 meters below the center of area to get to the center of pressure. So we have the magnitude of the force and the location. And if we needed to, we could do that same thing like in this previous example where we did a moment analysis to find what's the force required to hold the gate steady. We could do a similar thing here, but the problem wasn't asking that. It was just finding what's the force acting on the gate, not necessarily the force required to keep it closed. Okay, so any questions about this example?
Yeah, I'm having trouble get I like you did, I guess.
Okay.
I don't know.
All right, so let's see. A is the width parameter. So the width of the gate is 2 meters. And then B is the vertical distance, which is 3. Let me just double check with my calculator here. So it is 2 times 3 to the third power. So 3 to the third is 27. Multiply that by 2. So that's 54 divided by 12, 4.5. Yeah, 4.5 meters to the fourth. Are there other questions? All right. Well, getting the hang of these is all about practice. You know, the more practice we get, the easier it's going to become. So let's look at another example. Okay, now this time it's inclined. So this is our first example we're working together where we have an inclined gate. You can see that it's at a 45-degree angle. From the side view, we can tell that it's at a 45-degree angle. Now from the front view, we can see the width of the gate, but the front view doesn't directly tell us what is the height of the gate. We have to look at it from the side, because if we just measured the projected height, it doesn't look like 3 meters. It's only from the side view that we're able to see its actual physical height is 3 meters. So this is a 2x3 gate. Is that the same dimensions as this last one? Yeah. So it's that same 2x3 gate, but now this time it's at an angle. It's 5 meters vertically from the water surface down to the top edge. And let's go through the same step. Find the depth of the centroid, the magnitude of the force, the area moment of inertia, and the location of the force. Okay, so the centroid of a rectangular shape like this is just halfway in the middle horizontally, halfway vertically. So you could kind of, like if you've got this printed out, you could just draw a little black dot where the center of the area is for this shape. And we want to know the depth of the centroid. And so 1 is asking for the delta H, the vertical distance from the centroid to the water surface. So it's at a 45-degree angle. And the fact that it's at a 45-degree angle is going to mean that you can start to use your geometry. You know, the centroid is 1.5 meters from the edge. So if it has a total length of 3 meters, then that means that it's 1.5 meters here to the centroid. But that's an inclined distance. We want to know what's the vertical distance from the top edge down to the centroid, because problem subpoint 1 here, find the depth of the centroid, that means the vertical distance. So it's going to be 5 plus the vertical component of 1.5 meters. Let's see. Yes, KC, that's correct. You've got it. All right, so I'm going to stop talking, give you a moment to go through the calculations, confirm with your own calculator what KC has just found, that the depth of the centroid is 6.06 meters. Step 2, find the magnitude of the force. So magnitude is pressure at the centroid multiplied by the unit weight of the water. Area moment of inertia, that's going to be the same as our previous example. And then the location of the force. You're going to have to find the YCP, and it's going to be an inclined distance. And so it's the inclined distance from the water surface to where the force is applied. So you'll use the Y bar, use I divided by Y bar A. Okay, so he's asking about the water temperature. Yeah, it doesn't say the water temperature, and so since it doesn't specify, let's just use that the gamma is 9810 newtons per meter cubed. That's kind of the default unit weight that will be applied anytime a specific temperature isn't given. Example, you know, it becomes a little more complicated because of the geometry here. Since it's inclined, the overall structure of the solution is the same, but now we've thrown a sine of the angle into the mix. So let me show you how that affects things. All right. So, okay. The depth to the centroid is going to be 5 meters, and then the vertical component of the 1.5 meters that's at an angle. And so let's go back to the sketch just momentarily. Okay, so 1.5 meters from the top edge to the centroid is the inclined distance. So we want to know what's the vertical component of that 1.5 meters. So it's 1.5 meters from the edge to the center. We want to know what's the vertical component of that. So it's going to be less than 1.5 meters. Okay, so it's 1.5 multiplied by the sine of 45. So that tells us that delta H is 6.06 meters. And with that, we can find the magnitude of the force. So the magnitude of the force is the pressure at the centroid times the area, which the pressure at the centroid is delta H times gamma, multiplied by the area, and it turns a pressure into a force. All right, so the force is 356.7 kilonewtons. Okay, on part 1 and 2, is there any questions before we move further? It's best to resolve them now if there's still something that you're uncertain about. All right. You can see the formula for the area moment of inertia, and it's the same gate that we had in the example before this. It's just now it's inclined rather than being vertically oriented. So the fact that it is partially inclined doesn't change the area moment of inertia. That stays the same. All right, now look at the sketch that I'm saying the location to the force and how we find that, y bar. So if we have that the delta H is 6.06 meters, we want to know what's the inclined distance from the centroid to the water surface. So it's the vertical distance divided by the sine of 45 will give you the inclined distance from the centroid to the water surface. So 8.572 meters. All right, so that is the inclined distance to the centroid. And now we can substitute that into the formula for the center of pressure. Let me just zoom out a bit so we can see it in context. So it's the y bar plus the area moment of inertia times y bar times A. So the location of the hydrostatic force is going to be a little bit further beyond where the center of area is. And so that 0.087 meters means if you add that on top of the y bar that we had before, the YCP is 8.659 meters. So the geometry, it's a little bit tricky dusting that all off, but basically what you need to keep in mind is if this 3 meters is the physical distance of it, we want to know like the vertical component of the depth from the edge to the centroid. Oh, yeah. Degrees for the calculator. If you're working in radians, then you'll probably get a different answer. If you put in 45 and it's in radians mode, you should have 0.707. You're dividing by 0.707. Gavin asks, can we just take the slanted edge distance plus 1.5 to get y bar? All right, so can you find 1.5 is the inclined distance from the edge to the centroid. So I mean, yeah, you could do 1.5 plus, and now lengthen the 5 meters. So if it's 5 meters from the water surface to the top edge, what's the slant distance of that? That's going to be 5 divided by 0.707. So that's going to be 7.07 plus the 1.5, 8.572. It's the same. Yes, Gavin, you can do that. Are there other questions? All right. We are out of time for today. So what we will pick up and look at when we gather for our class meeting on Thursday is this one. It is another gate problem. It's an inclined flat surface. So just in the meantime, remember that you can get started on homework 3 even though you have a full week to work on it. You'll probably have a more comfortable experience the earlier you start. And then for those of you who are taking the Civil Engineering 319 lab, I'll see you this afternoon or tomorrow afternoon, and we're going to be taking a look at EPA-NET. So that's all for today. Hope you have a good one. I'll see you on Thursday.
Thank you.